Oh, okay. I'm audible. Fine. So, hello everyone. Welcome to a new stream. This is day 4, and I have to continue on this this particular theorem and all the exercises of this chapter. So, let's see if I can cover all of that in this stream. First of all, I would like to continue what was left in previous stream. I mean, revise. Sorry. Yeah. What did we see is what are definitions, theorems, and proofs? Okay. We saw about statements. A mathematical statement can be true or false. And if it is true, we make it a theorem. And from theorems, we make lemmas and corollaries. Lemma is basically when theorem becomes an NPC in this world. I kind of generalized, tried to make it a kind of mnemonic or what. So basically, lemma, just wait. Mathematical statements. All right. A theorem is a mathematical statement proved true. Generally, we reserve the use of that word for statements of special interest. Occasionally, we prove statements that are interesting only because they assist in the proof of another more significant statement. And such statements are called lemmas. So, when I say lemma is when theorem becomes an NPC in its world, I just mean that I'm using this particular theorem to prove a more significant statement. And what is a corollary? Corollary is also a theorem, but it is an argument that we make using a theorem. They come straight after theorem. For example, uh, let's say there is a theorem. Uh, what example can I take? For example, this right here. It was given to me to prove De Morgan's law. Okay, and I kind of proved it using some corollaries, which is of course wrong. This is not a proof. And then I continued to try proving it, but there was a weird contradiction I reached into, which was I was eventually trying to prove De Morgan's law using De Morgan's law. I saw some resources online and they also did that. So why is that? Um, so I got to know that this particular statement which I'm trying to prove the is under set theory De Morgan's law, and there is another De Morgan's law preceding that, which came before, and it is logical De Morgan's law. And proving logical De Morgan's law is very easy. You can just uh, make tables of gates, logical gates, and prove the formula. After you prove logical De Morgan's law, you can use that logical De Morgan's law with this, as you see in this box, right? This is basically I put a knot over this, and flip the sign in between. So basically, the application of De Morgan's law, and via this statement, we can eventually prove the set theory De Morgan's law. So that was very interesting thing I found. All right. Then this I have marked very, very, very important theorem. For every even number n greater than 2, there exist three regular graphs with n nodes. Okay, this was, I think, if I remember correctly, this was geometrical proof. Okay, when I was studying types of proofs. So eventually, The solution gave us three. This very interesting edge set of edges, and how this basically set was constructed is with this three different sets, union of these three different sets. And it was kind of very confusing at first how it actually visualized these three sets. But on stream, I then made this polygon. And when you see this polygon closely, what you see? I plus 1, I plus 1. And you do this for all. Uh, we can do 0 to 1. We can do 1 to 2, 2 to 3, 3 to 4, 4 to 5. But I plus 1. This won't cover the case. Okay. So this particular thing, the adjacent edges, by adjacent, of course, uh, I mean the adjacent nodes, edges made by connecting adjacent nodes. Okay, this will be left. So how can we build this? By this. Okay, and minus 1 comma 0. Then finally, we have to make the set of all diagonals. And to do that, uh, you can see this. You take the ith node and I plus n by 2, and it will eventually give you it will eventually give you the node and opposite node. So if you have I, then n by 2, basically you are halving whatever amount of points you have, half it, and then add the offset. The offset is ith node, right? So you loop from 0 to n by 2 minus 1 because you only need to take half of it, as other half will be covered via this formula. So 0 to 3, 0 comma 3, 1 comma 4, and 2 comma 5. This will also be covered. So taking union of all these three different sets, we get the set of all edges, right? And we prove that this set is a three regular set because each point here has a degree of 3, right? We're eventually constructing something to different groups. Here I try to understand this particular structure. Then what is proof by induction? There were two classifications made of proof by induction into basis and induction. Basis was something like I can relate to the step by saying like what is the term you take in recursive algorithms. There is a, I think, base step to which the recursion eventually reaches. But those analogies are different. Basis is basically contradiction, construction, induction. Basis. Every proof by induction consists of two parts, the basis and the induction step. Each part is an individual proof on its own. The basis proves that proof of one is true. I think this refers to statement P of one is true. The induction step proves that for I greater than one, if Pi is true, then so is Pi plus one. So you prove basis, and through basis, you eventually prove induction step. Every proof by induction consists of two. I covered that. Sorry. When we have proven both of these parts, the desired result follows, namely that P of I is true for each I. Why? First, we know that P of 1 is true because the basis alone proves it. Alright. Second, we know that P of 2 is true because the induction step proves that P of 1 is true, then P of 2 is true, and we already know that P of 1 is true. Third, we know that P of 3 is true because the induction step proves that P of 2 is true, and then P of 3 is true, and we already know P of 2 is true. This process continues for all natural numbers, showing P of 4 is true, P of 5 is true, and so on. Once you understand the preceding paragraph, you can easily understand variations and generalizations of the same idea. For example, the basis doesn't necessarily need to start with 1. It may start with any value b. In that case, the induction proof shows that p of k is true for every k that is at least b. In the induction step, the assumption that p of I is true is called induction hypothesis. Sometimes having the stronger induction hypothesis that P of j is true for every j is less than or equals to I is useful. The induction still, the induction proof still, wait, I think my chat is problems. Okay, fine. Okay. In the induction step, that is option K. I, I think I get the idea. Proof that P of 1 is true, then this is the basis step, induction step for every I greater than 1. Assume that P of I is true, and then use this assumption to show that P of I plus 1 is true. Let's prove by induction the correctness of the formula used to calculate the size of monthly payments and home mortgages. Um, okay. So we are doing a proof by induction. When buying a home, many people borrow some of the money needed for the purchase and repay this loan over a certain number of years. Typically, the terms of such payments stipulate that a fixed amount of money is paid each month to cover the interest as well as uh, part of original sum, so that the total is repaid in 30 years. The formula for calculating the size of monthly payments is shrouded in mystery, but actually is quite simple. It touches many people's lives, so you should find it interesting. We use induction to prove how it works, making it a good illustration of that technique. First we set up the names and meanings of several variables. Let P be principal. We have a variable P. By the way, dear viewer of mine uh, requested me to use a plain paper, so I'm doing so. Thank you. So we have a variable P, the amount of it is a principal, the amount of original loan. Okay. Then we have I greater than 0, yearly interest rate of the loan. Okay. Let Y be monthly payment. Y is the monthly payment. For convenience, we use I to define another variable M. We use I to define another variable M, the monthly multiplier. It is the rate at which the loan changes each month because of the interest on it. Following standard banking practice, the monthly interest is 1/12 of the annual rate. So M equals to 1 1 plus I by 12. Why am I writing 1 like that? I by 12. And the interest is paid monthly, monthly compounding. Two things happen each month. First, the amount of loan tends to increase because of the monthly multiplier. Second, the amount tends to decrease because of monthly payment. Let PT be the amount of the loan outstanding after the Tth month. Then P0 equals to P is the amount of original loan. Here we have PT is the amount of loan outstanding after Tth month. P0, the amount of original loan. P of 1 is the amount of loan after 1 month. And this series will continue. Is the amount of loan after 2 months and so on. Now we are ready to state and prove a theorem by induction on T. Gives the formula for value of PT. For T greater than equals to 0, we have the formula. Basis. Prove that the formula is true for T equals to 0. If T equals to 0, then formula states that, yeah, I can just say, if T equals to 0, that is basically the first case. P M0 minus Y. We can simplify right hand side by observing, of course, that M to power 0 equals to 1, 0. So simply P0 equals to P. Is our basis done already? Yeah. And then we have the induction step. K greater than 0, assume that the formula is true for T equals to K and show that it is true for T equals to K plus 1. The objective is to prove the induction hypothesis states that Pk will be equals to this, and our objective is to prove that Pk plus 1 will be equals to this. Fine. Basically, induction step says that P of K equals Pm K minus Y Mk minus minus 1 not to prove and how can we do that? We do so with the following steps. First, from the definition of pk plus 1 from pk, we know that pk plus 1 will be equals to this formula. Okay, this was basically this step. P1 equals to the concept. So I can say that pk plus 1 equals to p. What was that? P k m minus y. Therefore, we're using induction hypothesis to calculate pk. Have Oh, we actually expanded pk. Simply expanded it. So pk plus 1 equals pm. Okay. Multiplying through m and rewriting y. This will simply give us pmk plus 1. Just one more time. If I multiply here ym, and m will be multiplied inside as well. So yeah, it will yield us mk plus 1 minus m upon m minus 1. And this whole thing we have to subtract it with y. Or actually, okay, we can remove this parenthesis. Need a common. This is done. I think I want to understand this step some more because because let's say if we don't know the formula of compound interest and the reasoning behind it, then how can we eventually arrive at this step from the definition of pk plus 1? We know that. Okay. The basis of the interaction is true. I think as it is saying now, because we have defined p of not b to be p, this theory is important before trying to prove this formula. Okay, fine. Let's move to exercises. Yeah, so just a minute. My eyes are quite itchy today. Question one, we have to write formal descriptions of these sets. Sorry, for formal descriptions are given actually, and we have to write informal English description of informal English, right? So, I see on the first part as a simply set of odd numbers. Then it is a set of even integers. Then I see n equals to 2m for some m in n. A set of even natural numbers. Set of even natural numbers. Then I have w is a string of zeros and ones, and w equals reverse of w. W equals reverse of w. So it is talking about palindromes and string of zeros and ones. So set of all palindromic binary strings. Set of all palindromic binary strings. Uh, string is not heading right, but next part, W is a string of zero. Oh, sorry. Sorry. This part is right here. D part, n equals to 2m for some m in n, and n equals to 3k for some nnk. Okay, in n, okay, both are lying inside uh, n set, natural number set, and the members are multiples of LCM of 2 and 3, right? So 6 set of all multiples of 6. Yeah. Then finally in question 1, n is integer, n equals to n plus 1. N is an integer and n equals to n plus 1. Wait, what? N is an integer and n equals to n plus 1. This is not possible, bro. This set will simply be empty. Empty sets are called pi, I think. Okay, so question 2. Write formal descriptions of following. Okay, now oppose it. The set containing numbers 1, 10, and 100. I can write simple sets, right? Okay, so it will simply be 1, 10, 100. The set of all integers greater than 5. Set of all integers greater than 5. I think, write it like set of all integers which are greater than 5, and n belongs to integer. The set containing all natural numbers that are less than 5. Natural numbers that are less than 5. It is simply 1, 2, 3, and 4. That's it. The set containing string ABA. The set containing string ABA. Well, it's like, how can I write set builder form for this? String ABA should be part of the set. Let's say the set is A, such that string ABA belongs to A. Is that mathematically correct? I don't know, maybe I can write simply like some examples. Say ABA is one such example. Let's say A, comma, ABA, another example, etc. I don't know if I can write sets before set builder form. Next one, oh sorry, my face is cutting. E part, the set containing the empty string. It's like set A, and empty string is part of A. Well, I can interpret it two ways. It is a set that contains ABA, literal words. It is a set that contains ABA. Or It is a set, very big set that contains ABA somewhere. Okay, so I think both interpretations are correct. Then F part, the set containing nothing at all. Nothing at all, of course. This. Alright, now question 3. Let A be set XYZ, B be X comma Y. I have. Is A subset of B? Of course not. Is B subset of A? XY, XY, yes, it is. What is A union B? A union B is X, Y, Z. What is A intersection B? X, Y. What is A cross B? X, Y. Sorry. Yes, X, Y is a part, but I would like to follow my order. X, 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 Y. Now Y, X, Y, Y, Z, X, Z, Y. What is the power set of B? Power set of B, subset of all, a set of all subsets. Set of all subsets of B. It will be phi X, Y, X comma Y. And there are four elements, right? And 2 to the power 2, 4. So that's right. This is also done. If A has A elements and B has B elements, how many elements are in A cross B? Of course, just multiply them. A cross B, A times B. I mean, and I have to explain my answer also. So number of elements in A equals to A, number of elements in B equals to B. I have to find A cross B, number of elements, and I say that it is simply A times B, or I should actually write it simply like AB. Okay, because when can I prove this? You say there's three elements, two elements, six elements. One, two, three, four, five, six. Yes, I am correct. How can I prove this formula of cross product? Can't Then if I count the elements, I think that is called cardinality. Cross product. You need to show that there is a bijection with the set. This. In other words, you need to come up with a way to label the elements of the product and cross and with those numbers. A elements, right? So I'm going to write A. That's weird. Let's just rewrite things as MN. Much nice. If you count this, it is exactly n. Similarly, I think this is going to be n cross n. I mean, sorry, this is going to be n, and now this is going to be m. And so this is going to become a rectangle of m rows. Sorry, n columns and m rows. Oh, I can visualize now. A two. I don't need to write everything. A3 B1 A M B1. Ah, so here I have a simple rectangle, and that rectangle has that rectangle has n columns, m rows, number of cells will be simply m cross n, and that proves us easy. Next question is, if C is set with C elements, how many elements are in the power set of C? In power, you see number of subsets of any set is going to be whatever elements are inside 2 to power C, and power set is basically number of subsets, set of all subsets. So if you are asking me number of elements in power set, it is just number of subsets, which is this. I think I remember where I have studied this proof and I remember it. Let's say this C set has these elements. C element A1, A2 till AC. Okay, so overall C elements. Now to make a subset, you are allowed to take an element or take or not don't take it. So say take take yes and no. So two possible cases. Times take it, don't take it. Two times take it, don't take it, and so on. C times to power C. let x be the set and y be the set, the unary function, okay, and the binary function this are described in following tables. Okay, this question is now interesting. The level of questions are getting better. We have a function and we have another function. Okay. Oh, sorry, this is not function f, this is function g. What is the value of f of 2? Through this table, there is no 7, right? X gives y. You need to draw a table to actually find answers. N 6, 7, 6, 7, 6. G is even interesting. S- 10, 10, 10, 10, 10. Now we have 7, 8, 9, 10, 6, 7, 8, 8, 9, 9, 8, 7, 10, all 6. F of 2 equals to 7. What are the range and domain of F? Domain of F is this set. The range of F 6, 7. What is the value of G 2, comma 10? 2, comma 10, 6. What is the range and domain of G? Domain of G is basically the all possible cases. I mean, you have to cross product X and Y. This is going to be huge. 1 comma 6, 1 comma 7, 1 comma 8, 1 comma 9, 1 comma 10, and so 2, 3, 4, 5, comma 6, comma 6, comma 6, comma 6, 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5. And this is the complete set domain. And what is the range? This is going to be small, I think. I see 10, 7, 8, 9, 6, and that's it. What is the value of, okay, E part? What is the value of G 4 my f of 4? And I have f of 4 equals to 7. So it is equal to G 4 comma 7. And now 4 comma 7, I have 4, 7, 8. Answer is 8. Let's move to question number 7. For each part, give a relation that satisfies the condition. It should be reflexive and symmetric but not transitive. Reflexive and transitive but not symmetric. Symmetric and transitive but not reflexive. I mean, if you're asking me examples, then actually thinking out examples can be difficult. Unless I have to run my brain. Hmm. It should be R and symmetric, but not transitive. I don't know if that statement is even correct, which I wrote here. Reflexive is defined by it should all it should contain all the similar elements like a, comma b, and whatever. Give a relation that satisfies this condition. I can just take a set of let's take a set A, which is 1 comma 2 comma 3. I must take 1 comma 1, 2 comma 2, and 3 comma 3. This is already reflexive. To make it symmetric, let's say I take 2 comma 3. I should also take 3 comma 2. Now for transitive, I have 2 comma 3. I have 3 comma 2. Yeah, it should not be transitive. I must include some element that breaks transitivity. But what? See, here I have 3 comma 3. Here I have 3 comma 2. But do I have 3 comma man, no, no, no. What example can I take? Let's make an example first and then set around it. 1 comma 2. Here are two elements 1 and 2. So 1 and 1 and 2 comma 2 should be present. Take a case, there should be 1 comma 2. There should be 2 comma, let's say 7. 1 comma 7 should be present. So I must not include 1 comma 7. I put 1 comma 2. I put 2 comma 7. I put 7 comma 2, and there is no 1 comma 7. All right. So eventually my set is what? Let set A be equals to 1, 2, and 7. Right? Yes. Ah, there is no 7 comma 7, right? So 7 comma 7, just put it. I have these three elements 1 comma 2, 2 comma 1. If there is 1 comma 2, there should be 2 comma 1 present. Okay, 2 comma 7, 7 comma 2. So this set right here, this is reflexive and symmetric but not transitive. Read yourself. And I can actually replace 7 with 3, and this is fine. According to my 1 comma 2 comma 3 example. So thinking about result and then eventually making the set is quite easier than making a set first and building a relation out of it. So yeah, that relation is somewhat like comma 7, 7 comma 2, comma 2, 2 comma 1. This is the set. And how I prove that it is not the 1 comma 2, 2 comma 7, there is no 1 comma 7. Then a B part. Now the relation should be reflexive and transitive but not symmetric. Okay, I will take an example like 1 comma 1, 2 comma 2. Let's just say there is 2 comma 7. If there is 2 comma 7, 2 comma 2, 2 comma 7. Now say there is 1 comma 2 and now there is 2 comma 7. They must be present 1 comma 7. Fine. Now the set is what? The set contains 1, 2 and 7. Okay. We have 1 comma 1, we have 2 comma 2, we have 7 comma 7. Now 1, 2, we don't have 2 comma 1, so it is not symmetric eventually. But is it transitive? Oh wait, I forgot one. No, no, it's fine. We should not make it transitive anyway. We have 1 comma 1, we have 1 comma 2, so we should have 1 comma 2. Yes, we have 2 comma 2, 2 comma 7. We have, okay, we have 1 comma 2, 2 comma 7, then 1 comma 7. Yes, is we correct. Fine. So this relation is as there is no 7 comma 2 present or 7 comma 1 present. This is not symmetric. Now symmetric and transitive but not reflexive. Let's make this relation. This should be symmetric and transitive but not reflexive. Let's take the same example of 1 to 7. Okay. We will make a set such that we have 1 comma 2, we have 2 comma 1, we must have 1 comma 1, and I think that is fine. This relation is not reflexive, of course, because we don't see 2 comma 2, but it is transitive eventually because we have 1 comma 2. Okay, okay, yes, yes, it's fine. This relation already satisfies. Now, question number 8. Consider the undirected graph G where V is 1, 2, 3, 4 and E is 1 comma 2 comma 3 1 comma 3 2 comma 4 and 1 comma 4. So let's make 1, 2, 3, 4. Connect 1 and 2. Connect 2 and 3. Connect 1 and 3. Connect 2 and 4. Connect 1 and 4. Indicate a path from what are degrees of each node. Okay. Degree of this node is 1, 2, 3. Degree of this node is 1, 2, 3. This node is 2 and this node is 2. Indicate a path from node 3 to node 4. Node 3 to node 4 on your drawing of chi. Will be the path. Question was this one. Draw the graph of G. I made it. What are degrees of each node? I wrote. Indicate a path from node 3 to node 4 on your drawing of G. Done. Write a formal description of following graph. Okay. We have a graph G with some vertex and edges, and V is a set of 1, 2, 3, 4, 5, 6, and E is a set of, I see connection between 1 and 4. I see connection between 1 and 5 and 1 and 6. Then 2, 4, 2, 5, 2, 6. Then 3, 4, 3, 5, 3, 6. Then proof questions. Find the error in following proof that 2 equals to 1. Consider the equation A equals to B. Multiply both sides by A to obtain A square equals to AB. Subtract B square from both sides. Now factor each side. Array. Divide each side by A minus B to get A plus B equals to B. Let A and B be equal to 1. You say 1 equals to 2. What mathematical principle are we violating here? You can't simply divide. Oh. I think this division step is wrong. Oh, this is always going to be positive. At b square. B square is always going to be positive. I don't know about so this term is always going to be negative. Possible. When you are dividing both sides by a minus b, can you actually confirm me that it is not going to be divided by 0? Can be divided by 0, right? Maybe you can subtract a plus b from both sides, but not a minus b. You should write it fully. Like here you actually see 1, 1, 1 comma 1, 0, 1 comma 1, 0. I should write this. Okay, there is a series of n elements. This is sum of natural numbers. Let another series be cube of cubes. Prove the following equalities by induction to n. Arrive at the curious conclusion that Cn is equal to s square n. I mean, let's say I take C2 will be equal to 8 plus 1, 9. Okay, and s square of n. Take 3. Okay, 3 square. Yeah, you are right. Well, there are two formulas here that I have to prove. When I'm talking about induction, I'll just take the first basis step, like s of 1 that is equal to 1 by 2, 1 plus 1, 2, and it is equal to 1. So s of 1 is equal to 1. Now, hypothesis. We take, we generalize this by using k half, and then we have to prove k plus 1 equals to if we are able to prove this step, then I think induction will be completed. If I we have to write this function in the form of this function. If I go to the basics, this will be equal to 1 plus 2 plus till k plus 1, right? And this part is actually sk. So sk plus k plus 1. I can expand this half k plus 1 plus k plus 1 k. Let's take this part common. I have then I have k plus 1 by 3k plus 2. Yes. Two. Multiplying should give me 2 and adding or subtracting should give me 3. 1. Yes. Yes, it's done. Induction by proof completed successfully. I should save this document. Cn is equal to 1 by 4 of n to power 4 plus 2n cubed plus n square. You see this thing right here? If you see this, it is equal to half n plus 1 whole squared, which is eventually Sn squared. How to arrive at this conclusion? Prove the basis C. It is eventually 1. C1 equals to 1. So I say Ck is equal to 1 by 4 k squared k plus 1 squared. Now I have to prove the statement C k plus 1. So to write this function in the form of this function, to basics, this is equal to 1 cube plus 2 cube plus so on till k cube plus k plus 1 cubed, right? And this part is precisely equals to c k. So c k plus 1 is equal to c k plus k plus 1 cubed. C k is equal to that part 1 by 4 k squared k plus 1 squared plus k plus 1 cubed. I should expand it. K square k to the power 4 plus 2k cubed plus k square plus 4 times k plus 1 cubed. K cubed plus 3k plus 3k square plus 1, and all of this should be multiplied by 4. So this is multiplied by 4 k to the power 4 k cube 6k cube square terms 13k square plus 12k plus 4. 1 by 4 times the shit. K square plus 1 2k. I can prove reverse. K plus 1 squared, k plus 2 squared, k square plus k plus 1, k square plus 4k plus k to the power 4, 4k cube, 4k square, k cube, 8k square, 8k, k square plus 4k plus 4. So we get k to the power 4. For k cube, there's 4 plus 2, 6 plus 6. For k square, we have 4 plus 8, 12, 12 plus 1, 13. For k, we have 8k plus for 12k, eventually 4. So yeah, this is eventually equals to thus ck plus 1 is equal to 1 by 4 k plus 1 squared k plus 2 squared, hence proved by induction. Next question is find the error in following proof that all horses are the same color. Okay. The claim is that The claim is that in any set of H horses, all horses are the same color. Proof by induction on H. H equals to 1 in any set containing just one horse. All horses clearly are the same color. Induction step for k is greater than 1. Assume that the claim for h equals to k and proves that it is true for hk equals to k plus 1. Like any set capital H of k plus 1 horses, we show that that all the horses in this set are same color. Remove one horse from this set to obtain set H1 with just k horses. By the induction hypothesis, all the horses in H1 are same color. Now replace the removed horse and remove a different one to obtain the set of set H2. By same argument, all horses in H2 are same color. Therefore, all horses in H must be same color. And proof is complete. And we have to find error in this proof. Well, this question is interesting. Basis we took just one horse, and as it is just one horse for same color, so basis is true. Now for k equals to 1, um, I take k. Let's say the claim is true for k horses, and we add another horse. It should be same color. Remove one horse from this set to obtain the set H1 with just k horses. By induction hypothesis, all the horses in H1 are the same color. Okay. Well, you are here, right? It's okay. I take a horse. Horse number one. Okay. And I just say, okay, it has a color, fine by me. Then I claim that this basis is true for k elements. Okay. I take k horses. And I say this claim is true for all horses, all k horses. That means all k horses here are same color. Okay, that's fine. Now we have to add another horse. We say H1, H2 till HK and HK plus 1. Now, the new horse which you added, you can never be sure, right, that this is going to be same color. It is going to be same color, right? So I think this claim is wrong here itself, that you are taking any random horse, remove one horse from the set to obtain H1. That was my alarm. Hmm. Horses in H1 are the same color. I remove one horse. Let's just say I removed H2. Okay. Replace the removed horse and remove different one to obtain the set H2. All horses in H2 are same color. Okay, this proof is totally wrong. You know what it is saying me? It is saying me that H1, okay, by the basis, this horse, same color. This horse, same color. I mean, you're just looking at one horse, bro, and you're saying all horses are same color. This way of checking is wrong, but how can I write it? I mean, this proof is wrong because you can never know if H k plus 1 is of same color as others. Okay, and I don't know if how to write this formally. I should search this question online for, let's say, some answer. Well, you know what? Um, the way it is telling me to write the sets like H1 equals to take one element, remove this element. I was wrong there. Okay. H1 is K horses. But when you actually arrive at HK, H minus HK, no. I think you're wrong here because you don't know, right? If HK plus 1 is going to be same color as all of the others. So, I mean, this claim itself is wrong. And thus all claims are wrong. The only claim which is going to be true is HK plus 1 element, which is uh, uh and subtract. Because I have defined HK plus 1 already. Actually, I should not write it as HK plus 1. I should just write it HK on the H, I mean. h equals to this, and hk plus 1 equals to h minus hk plus 1, and this is going to be true. Only this statement is going to be true and rest all statements are false. Let's search this question online. Google.com. Can I simply paste? No. Proof relies on the overlap between two subsets H1 and H2 to transfer the color property from one horse to another. When H equals to 1, moving to a set H of k plus 1 is two horses. Let's call the horses A and B. Removing horse B leaves H1A. By hypothesis, all horses in H1 are same color. Okay. No overlap. For the logic to hold, there must be a common horse in both H1 and H2 to link the colors of A and B. Because this is why when k plus 1 is equal to 2, there is no overlapping horse to force horse A and horse B to share the same color. Therefore, the induction step breaks down at the very first step, equals to 1. But instead of taking two elements, you should actually take key elements and then prove. But then also, suppose a set of one horse. Obviously, all the horses in set are same since there is only one horse. Next question. Mistake is in the inductive step. The reasoning assumes that there is horse 1 that you can remove, leaving you with set of k horses that by inductive hypothesis all share the same color. Okay, so far so good, but then it says we can put horse 1 back and remove horse 2, and so this new set k horses have the same color as well, also good. But why doesn't this show that all k plus 1 horses have same color? Because if k equals to 1, horse 1 and 2 are only two horses. And yes, removing horse 1 leaves all remaining horses, which is just horse 2. It's the same color, and same goes for horse 2. Of course, the reasoning would go through k greater than 1. For then you would have a horse 2, horse 3 that when horse 1 is removed must have same color as horse 2, and that when horse 2 is removed must have same color as horse 1, and any other horses would indeed have to have the same color. But of course, if you assume that any two horses always have same color, then obviously any sized group of horses will have same color. So it is really just that one case with two horses that is the crucial case, and neither the base case nor the inductive step cover that case. Or to be exact, the base doesn't cover it at all, and the reasoning in the inductive step fails for that particular case. The induction says that I has n horses, so so far the induction step is good, but then it assumes that M is not empty and that there is distinct color for all the horses in M, and that color is that must both be. But if M is empty and does not follow, all horses of M are Vk same color as horse 1. M is empty for not empty, but true. But n equals to 1 just happens to be our base case. So our induction step doesn't work for our base case. And if it doesn't work for our base case, then the proof fails. So kind of, you know, our base case itself is wrong. I was actually saying something like this is wrong, but base itself is wrong because you are not comparing. To compare two horses, you must have two elements, but there's always one element. Intersection is always going to be null. Okay. Next question. Show that every graph with two or more nodes contains two nodes that have equal degrees. Ramsey's theorem. Selected solutions. Okay. I have three more questions to go. Every graph with two or more nodes contains two nodes that have equal degrees. Two or more nodes. Let's say I made three nodes. Every graph with two or more nodes contains two nodes that have equal degrees. If I connect this and this, you see this node and this node have equal degree. Well, by construction, I can definitely prove that. I will make a graph G that of course is made up of V comma K, where V will be, let's say, a set such that this V set will contain the element n, such that n belongs to natural number and n is greater than or equal to 2. And K, this is going to be interesting. Construct all possible solutions. You have to remember that circle, right? I don't know how to prove this. I think by geometry, I can only say By geometry, I can only say something like um, I can consider all possibilities, but to actually see, I can, I'm not able to think of any solution. Well, it is just obvious to the mind, but mathematics, we don't go on intuition and obvious things. Okay, we have to prove. Ramsey's theorem, let G be a graph. A clique in G is a subgraph in which every two nodes are connected by an edge. An anti-clique, also called independent set. Anti-clique is also called independent set, is a subgraph in which every two nodes are not connected by edge. Show that every graph with n nodes contains either a clique or an anti-clique with at least this much nodes. Okay, this is so interesting. Use theorem 0.25 to derive a formula for calculating the size of the monthly payment, principal P, interest rate I, and the number of payments T. Assume that after T payments have been made, the loan amount is reduced to zero. Use the formula to calculate the dollar amount of each month payment for a 30-year mortgage with 360 monthly payments on an initial loan amount of $100,000 with a 5% annual interest rate. Well, for question 13, show that every graph with two or more nodes, every graph with two or more nodes contains two nodes that have equal degrees. However, a graph cannot simultaneously contain a node connected to every other node and a completely isolated node. This restricts the possible degree of values to set of size n minus one, meaning two nodes must share a degree by pigeonhole principle. Proof by pigeonhole principle. Let n be total number of nodes in graph of n greater than 2. Okay. In any simple graph with n nodes, the degree of any node is an integer between 2 and n minus 1 inclusive. Okay. Mutually exclusive extremes. The node of degree 0 means it is connected to no other nodes. Node of degree n minus 1 means it is connected to all the other n minus 1 nodes. These two state that both cannot happen in the same graph, because if one node connects to all others, no node can have zero neighbors. Because cannot both exist, the set of actual degrees for the n nodes must come from restricted pool of size n minus 1. Since we have n nodes and only n minus 1 possible degree values, at least two nodes must share same degree because there are n nodes. Okay, okay. So by pigeonhole principle, wow, if there are let's say three space and four pigeons, four pigeons, then to fill all the boxes, you must put one you must fill one box with two pigeons. Then only you can fit all boxes, right? So by the same principle, by the same principle, if there are n nodes, the degrees are going to be like the set of 1 to n minus 1. Then only n minus 1 nodes are covered, right? So other node, it's just not possible that it will have 0 degree, though, because both cannot coexist. That means some other node must have some degree with in this range. And if it has a degree within this range, then of course two nodes have same degree. Oh, beautiful, beautiful, very beautiful. 14. Make space for two piles of nodes A and B. Then starting with the entire graph, repeatedly add each remaining node X. It is something called Ramsey's theorem. It says that show that every graph with n nodes contains either a clique or an anti-clique with at least this much nodes. How did you even discover that number? This is so amazing. Let G be a graph. Oh, I have made one statement wrong with at least. No, at least word is important. Leak means every pair of vertices is not connected means no pair of vertices is connected. Vertices ABC form a clique, but adding D breaks the completeness since D is not connected to all other nodes. So the entire graph is not a clique. Graph with two cliques. Any graph or its complement graph has a clique with at least logarithmic number of vertices. Proof of two color, proof by two colors is, what is this two colors case? Ramsey's theorem on graphs. Imagine you have six people at a party. We assume that for every pair of them, either they know each other or neither of them knows each other. So we are assuming that X knows Y and Y knows X. And we claim that either there are at least three people, all of whom know each other, or there are at least three people, no two of them know each other. Okay, let's say we have proof of claim. Consider P6 among the five people. Either there are at least three people that P6 knows, or there are at least three people that P6 doesn't know. Why is this? Because suppose that among other five people, there are at most two people that P6 knows, and at most two people that P6 does not know. Then there are only four people that other than P6, which contradicts the fact that there are five people other than six. If P1 knows P2, then P1, P2, and P6 all know one another. I think I should cover this theorem in a video because it will take me time and I have to go to college today. Might get late if I don't stop the stream now. What was the last question? Using theorem 2.0.25. 0.25. This is the theorem. Payment after T days will be equal to this. Prove that via induction. And now we have to use this theorem to derive a formula for calculating the size of monthly payment for mortgage in terms of principal P, interest rate I, and number of payments T. Assume that T payments have been made, the loan amount is reduced to zero, and we have to use this formula to calculate the dollar amount of each monthly payment for 30-year mortgage with. Don't you think we already have that formula? 360 monthly payments on an initial loan amount of 5% annual interest rate. I'm thinking I will continue the Ramses theorem in this PDF itself, and in a new PDF, I will for this question. Then we can finally move to the new chapter. I think that is it for stream today. Much time? 2 hour 22 minutes. Thank you for joining the stream today. In next stream, we will cover final two questions because I need a lot of time, I think, to cover these questions. And uh, I have to go to college right now, sadly. Bye.